Okay, let's do a little bit more practice with limits because I think limits are really important and there's going to be lots of chances for us to get better at it. Okay, as always, make sure that you use the pause button when you're studying. Try to do as much as you can by yourself. The more that you do by this yourself, the better that you're going to be. And we want you to be the best. Okay, so let's start with a multiple choice question. So we're given that the limit as x goes to a of f of x plus g of x converges. And limit as x goes to a of f of x minus g of x converges. So in other words, if I add the values together or if I subtract, I get something which converges. The question is, what can we conclude about the limit as x goes to a of f of x and limit as x goes to a of g of x? So there's a couple of options. One is they both must converge. Another option is it is possible that they both do not converge. And the last option is we don't have enough information to make any conclusions. Okay, well, one thing that's nice about this problem is we have a 1 in 3 chance that we're going to get the right answer. So, woohoo! Good odds for us. But in fact, I think we can do better than 1 out of 3. So what's our idea here? Well, the question is, can we figure out something about f of x given these pieces of information, namely the sum of f plus g, the difference of f minus g? So one of the things we can do is we can say, well, let's look at ways to rewrite and combine things. Notice if I look at f plus g and f minus g, what are some ways I can combine those together? And in particular, ways that are compatible with limits. Well, limits work really well with things like addition and scaling. So notice there's a really nice thing to note. See, f of x, I can write that as f of x plus g of x, and then I'm going to add f of x minus g of x. Now, I'm not done writing stuff down, but notice what happens. The g of x's cancel. What's wrong? Well, I end up with actually a factor of 2, right? Because there's 2 f of x's. But now, I can say there's a half. So what do we get? Well, that says f is a combination of f plus g and f minus g. So what does that tell me? Well, it tells me that the limit as x goes to a of f of x is the limit as x goes to a of all this expression, 1/2 f of x plus g of x plus 1/2 f of x minus g of x. Right? It is, yeah. And now we can say, oh, I can break up over addition and I can pull out factors as long as I know that the limits themselves exist. And I know that they exist. See, when we say the word converge is a way of saying that the limit goes to something. In other words, it's equal to some value. So this is equal to 1/2 limit as x goes to a of f of x plus g of x plus 1/2 limit as x goes to a of f of x minus g of x. And now we're in our happy space because this goes to something, converges, and this other piece goes to something because it converges. And therefore our conclusion is that this also converges because it has to go to something. So f has to converge. But not just f, if you do a similar argument, you can show that g also has to converge, and therefore the answer is A. They both must converge. Good. All right. Let's do another problem, another word problem, which is going to be a little bit similar. Okay. Given the limit as x goes to 2 of f of x plus g of x equals 5, okay, so it also converges, and limit as x goes to 2 of g of x does not converge, what can we conclude about the limit as x goes to 2 of f of x? All right, this one's a thinker. We know that when we add them together, the result has to be 5. And we know that g of x doesn't converge. Well, I have to get to 5 somehow. Maybe it's the case that limit as x goes to 2 is 5. Well, maybe. Maybe it's the case that the function converges. Well, we know that the sum converges, so something's converging. But there's not information to say what it converges to. Possible. Maybe it's the case that the limit as x goes to 2 of f of x does not converge. Okay. Maybe it's a situation that can never happen. All right, well, maybe it's impossible for the sum to converge, but one of the individual pieces to not converge. And the last thing is, we don't know. We don't have enough information to make any conclusions. Really, it's kind of like a none of the above. Okay. Well, the previous one had 3 options. This one has 5, so it's a little bit harder to just randomly guess and get the right one. So now we have to ask ourselves a question. Can we say anything definitively? Well, what do we know? Well, there's a couple of things. We can say, look, I know something about f plus g, and I know something about g, and I'm trying to figure out something about f. And so really, it's kind of a silly thing to write down, but you might as well write down, look, I know that f of x plus g of x is f of x plus g of x. Okay, but what I really want to emphasize is there's the piece as a whole, and then there's the individual pieces that we're looking at. So we can say to ourselves, okay, what must be true? Well, we're trying to figure out what's happening to our function f. Now, one of the things we can say is, look, there's 2 possibilities. So I'll draw the 2 possibilities as a box. And we're going to look at it, and we're going to say, look, one possibility is that the limit of f converges. So that means that there is a limit. And another possibility is that the limit of f diverges. And so that means it doesn't converge. And so, all right, so the question is, well, which box do I put it in? And is there a unique box? Maybe in some cases it goes in one box, maybe in some cases it goes in the other box. But I'm suspicious about something, because I get a feeling here that the fact that g of x doesn't converge means that there's a problem. And if I have a problem, I somehow can't take something which doesn't have a problem, combine together with something which does have a problem, and then somehow everything works. Something doesn't feel right. So let's think about this. Let's ask ourselves a question. Is it possible that I might be inside of this box? All right, so suppose that the limit as x went to 2 of f of x converges. Okay, we can always assume anything we want. We have to justify our assumption at some point, but for now, let's just suppose, and let's explore what happens when we make that assumption. Well, what can we do? Well, so what do we have? We know that that piece, f of x plus g of x, converges, and that piece converges. So what we can do is we can do a little bit of moving around. We can say, hey, you know, g of x is f of x plus g of x minus g of x. Oops, sorry, minus, typo, minus f of x. There we go. All right, now we throw in the limit. So the limit as x goes to 2 of g of x, because these limits individually converge, because we know that this is our assumption it converges, and we were told that the sum converges, then that's the limit as x goes to 2 of f of x plus g of x, and minus the limit as x goes to 2 of f of x. Well, the first part we're happy with. And by when I say we're happy, we mean converges. The second part we're also happy with. It also converges. And therefore, this is converging. Now, what's wrong? We were explicitly told the limit as x goes to 2 of g of x does not converge. So if we were in this box, we'd reach an impossible situation where something did converge and did not converge. Converge and not converge, it's binary. You're one or the other. There's no like, I might converge every other Tuesday and maybe on the 4th of July. No, that's not how it works. Okay, so we're not inside of here, which means I can eliminate this as a possibility. So that means I have to be the case that the limit of the function is diverging, which means that the answer is C. Now you might say, wait a second, hold on. Is it possible that this situation can even happen? And the answer is actually yes. It's not so hard to come up with a function. And here's kind of a silly pair of functions. But you know what? When you're thinking of examples, start with silly examples and then work your way up. So make your function f look like the following. It's 0 before 2, and then it's 5 after 2. Okay? So there's our function f. What's our function g? Our function g is going to do the opposite. It's 5 before 2, and it's 0 after 2. Now what happens? Well, when you add f plus g, you always get 5. Except at 2 where you haven't bothered to define it, and that's all right. We don't care about what happens at 2 when we're taking limits. So it definitely can happen. And it's good to try to say, can it happen? What are some examples? And you don't need very many examples. Very simple things just like step functions, or you can have a line with a single point off. Oftentimes just really simple examples are enough to get you going and get you started. All right, let's actually do some limits, not just ideas. Let's do some algebra. Oh, algebra, sweet, sweet algebra, I've missed you. Well, it hasn't been that long. Okay, so find the limit as x goes to 2 of something. This is good. Square root of x squared plus 5 minus x minus 1 divided by x plus 1 times x plus 2 minus 6x. Now the first thing we should always try whenever we're encountering a limit for the first time is ask ourselves the question, what would happen if we plugged in our limit points? In other words, what happens when we plug in 2? Well, let's find out what happens when we plug in 2. So this is going to upstairs. 2 squared is 4 plus 5, so that's square root of 9. And then minus 2 minus 1, that's, I'll put that as minus 3. Then downstairs you have 2 plus 1, which is 3. 2 plus 2, which is 4, so 3 times 4. And 6 times 2 is 12. And if we simplify, we're going to get 0 upstairs, 0 downstairs, 0 over 0, which of course means, that's right, more work. More work. Exactly. All right, so where's our work? Well, when we see algebraic expressions like this, our mindset is, let's look for ways to get some cancellation. In particular, because we're doing a limit as x goes to 2, we're going to think of, let's try to find some x minus 2's floating around to get some cancellation out. Now downstairs, it's probably not going to be too bad to figure out where to find an x minus 2. Upstairs, we've got to think about how to get rid of the square root. Because until we get rid of that square root, we're not going to find an x minus 2 there. Now this is going to require a little bit of thought, but that's okay. We have time to think about this. We're not under stress. We have plenty of time. Plenty of time, I hope. Okay. So how do you get rid of square roots? Well, the answer is you're going to multiply by the conjugate. Now let's be a little bit careful here. Because notice what we have here. We have the square root of x squared plus 5 minus x minus 1. Now, if you count, there's 1, 2, 3. 3 terms. But when we're talking about conjugates, what we want is we want to start with a minus b, and then we want to get to a plus b. So the question is, how do we get from 3 terms to 2 terms? And what's the right way to do it? So the way to do it, in fact, the only way available to us, is to group. So in other words, we want to group 2 of these things together and another thing by itself. Now, how do you group? Well, the answer is you want to group in a smart way. Well, how's a smart way? What makes something a smart way? Our ultimate goal is to get rid of the square root. So we want to group in such a way that the square root is going to be one of the things that end up being squared. So this piece right here, this should be by itself. And these two pieces, we should put them together. So what I'm going to do is I'm going to put a little parenthesis here. Minus, and we're going to, now be careful, be careful. What happens to that minus? It becomes a plus. So here's our A and our B. All right, so when we multiply by the conjugate, we're going to multiply by the square root of x squared plus 5 plus x plus 1. All right, so that's, keep that in mind. Okay, so, well, let's begin. So that's just a little sort of side note for us. So we have the limit as x goes to 2 of, I'm just copying down, square root of x plus square root of x squared plus 5 minus, and I'll write it in this form right here just to make it easier for me to remind myself. Downstairs, well, I won't do anything yet, but it's coming. I'll do some stuff downstairs. All right, so to help us get rid of the square root upstairs, multiply square root of x squared plus 5 plus x plus 1. And if you multiply on the top, you need to also multiply on the bottom. Remember, whatever you do, you have to make sure that the expression that you get to is equivalent to the expression you started with. If you end up with a different expression, you're doing a different problem, and you're not going to get the right answer. So that's why we always multiply by the top and the bottom. Because you're multiplying by 1, it's the same problem. And that's good. We want to be working on the same problem. Now, what happens? Well, we're still taking the limit. That hasn't changed yet. Now, upstairs, we're going to have a squared, x squared plus 5, minus b squared. So that's x plus 1 squared. Downstairs, we don't want to multiply these terms out because that'll take us a lot of time and it won't give us anything. You see this, the conjugate only gives it to the place where it's actually having that a minus b times a plus b. In the other part, in other words, the top or the bottom, wherever that other piece ends up, it's not helping you, and you don't want to multiply it out because that's going to take time and frustrate us. We don't want to be frustrated. That's not what mathematicians do. Well, let's, all right, so we'll still save that for our next step. X plus 1 times x plus 2 minus 6x times square root of x squared plus 5 plus x plus 1. I've gone ahead and dropped the parenthesis, but that's okay. Now, we start on our cleanup. Upstairs, x squared plus 5 minus, and then we square that out, x squared plus 2x plus 1. Good. Downstairs, well, there's not much we can do with the second piece, but the first piece we can manipulate it by expanding. So it would be x squared, then we have plus 2x plus x, so that's plus 3x, plus 2, then minus 6x. And then we have, of course, the square root of x squared plus 5 plus x plus 1. All right, now, this is our sort of moment of truth. We're going to clean up a little bit, and, well, not yet. Our next step is our moment of truth. So hold on. Limit as x goes to 2, and x squared minus x squared. Gone. Then we have a, there's no x here, but here there's a minus 2x, so minus 2x, 5 minus 1. So don't forget the minus goes through, so that's why it's a minus 2x minus 1. So plus 4. Downstairs, oh, there's a lot downstairs. There's an x squared, 3x minus 6x is minus 3x, and then plus 2. And of course, this other piece on the end. Square root of x squared plus 5 plus x plus 1. All right, now, when I say the moment of truth, what should happen? You see we got 0 over 0, which means that there had to be things which caused us to have a 0. Now, generally speaking, when you have algebraic expressions, the things that are causing you to have a 0 are things like x minus a. So we're looking for x minus a. In our case, x minus 2. So let's look upstairs. Do I have something that looks like x minus 2? Well, if we factor out the minus 2, it is, in fact, an x minus 2 upstairs. So limit as x goes to 2, minus 2 times x minus 2. Now, downstairs, x squared minus 3x plus 2. Does it factor? It does. Is one of the factors x minus 2? It is. It is. Now, you might hesitate. How do you know that? Well, I've lived a good, clean algebra life, just like you, of course. And I can anticipate. But another way you can check is plug in 2. 4 minus 6 plus 2 is 0. Or you might say, hey, I've seen this. Once you hang out around algebra often enough, you start to say, whoa, wait a second, I've seen you before. You're like, yep, I have. And of course, don't forget parenthesis. Now, this is the satisfying part. We know we were getting 0 over 0. We've now gotten to the point where we can cancel the things which were causing the 0 over 0. And therefore, we've made progress. Important progress. We've gotten to the point where we can now make something where we don't get 0 over 0. Okay, so I'm going to rewrite it one more time. Not that I really have to, but just because I just want to show you what it looks like. So minus 2 over x minus 1, square root of x squared plus 5 plus x plus 1. So we haven't taken any limits yet. Most of the work here is involved in rewriting what we have. So we were able to rewrite our algebraic expression into something more convenient for us to work with. And now we plug in our value. We plug in 2. Notice the top is definitely not going to be 0, so we're going to get a nice answer. At least we're going to get an answer. Because I'm now taking the limit, I don't write the limit down. See, I've been writing the limit down, and now I'm taking the limit, so I don't need to write it down anymore. So, negative 2 upstairs over, here we have 2 minus 1. That's 1. Times square root of 2 squared plus 5. Well, that would be square root of 9, which is 3 plus 2 plus 1. So that would be 1 times 6. Okay, so we end up with negative 2 over 6 or negative 1 over 3. And we're done. Good times. Good times. Well, we had to work it through. We had to be patient, and we're rewarded for our patience. We got a nice number. We got a nice number. Good. All right. Well, that was algebra. Time for some trick. We always want to balance it out, right? You've had a little bit of algebra. You want to balance it out with a little bit of trick. It's good to have a well-balanced diet of math problems. Okay. So, find the limit as theta goes to pi over 6. So, see, this is a more interesting angle. It's not just 0 or pi. Pi over 6. And what is it? 1 minus 2 sine theta. Upstairs, downstairs, 2 root 3 cosine theta minus 3. Now, well, what does this become? So the first thing is, let's just check and see if it becomes something nice or not. So we have, when we plug in pi over 6, well, we know sine of pi over 6. Well, I say we know it because it's written down. Sine of pi over 6 is a half. So upstairs we get 1 minus 2 times a half, which is 0. How about downstairs? What do we get? Well, cosine of pi over 6 is root 3 over 2. If you multiply 2 root 3 times root 3 over 2, you're going to end up with a 3. Minus 3 is 0. So we end up with 0 over 0. And of course, 0 over 0 is the universal sign for more work. So we need to do something to figure out what's going on. Well, what do we do? Well, we're going to cancel. That's basically our tool right now. We will have more tools, by the way. It's not the end of our tools. But it's really a good tool. If you're getting 0 over 0, there's a good chance for cancellation to be happening. So what we have to do is sort of start looking for cancellation. So we say to ourselves, all right, what can we do? Now, when we look at this, we say that the numerator and denominator, they're both trig, but they're kind of different functions, right? Because one of them is the sine and one of them is the cosine. It's like comparing apples to other types of apples. But they're not really quite the same. We would really be much happier if they were more similar to one another. So is there a way for us to take, say, the sine function and replace it with the cosine function? Well, in this case, there's a nice identity to keep in mind. So our identity in the back of our head is sine squared plus cosine squared is 1. It's a good identity to keep in the back of your head. So we say, okay, sine squared plus cosine squared equals 1. So if one of these were squared, we could do some rewriting. But they're not. Yet. Not yet. So now we have our how can I rewrite these so I can make something into a square? So we start thinking and say, is there any tool that we have that helps us introduce squares? And if you're thinking conjugation, you got it. That's what we want. So we want to do some conjugation here. Now, the question is, do we conjugate on the top or do we conjugate on the bottom? And the answer is yes. Now, when I say yes, I don't mean both. I mean, you can pick one. This is a situation where you have options. So I'll do it on the top, mostly because I'm a little bit nervous about doing lots of stuff involving the cubed root of 3. Not because cubed root of 3 is a terrible number, but just because I know I make mistakes. And I've learned that one of the best things for me to do to avoid making mistakes is try to keep the computation simple. So when I have an option, I always ask myself, what's the simplest option? The one where I'm least likely to make mistakes. So I'm multiplying by the conjugate on the top. And again, the long-term plan is if I can get a sine squared, that tells me there's a cosine squared waiting, which means I have a chance. Okay, so what does this become? Limit theta goes to pi over 6. Upstairs we're going to get 1 minus 4 sine squared theta. Now where is that coming from? Well, it's coming from a squared, where a is 1, minus b squared, where b is 2 sine theta. Now downstairs, what do? You don't expand. Leave them as separate. Remember, when you're doing conjugates, only expand where you actually used it. In other words, you don't expand on both top and bottom, just on the side where you're using the conjugate to make progress. Now, again, remember our goal. We want to get the sine squared replaced by the cosine squared. So this is the limit as theta goes to pi over 6 of 1 minus 4 times, parenthesis, 1 minus cosine squared. All right. You're probably thinking, boy, there's a lot of algebra going on for this trig type problem. Algebra's good. We should do more algebra. Because if we get really good at algebra, calculus is going to be fun. And don't we want calculus to be fun? Of course we do. What a silly question. All right, so now let's be careful here. What do we have? So we're going to expand the minus 4 through. And let's see, that would become the limit as theta goes to pi over 6. That's always there. We haven't taken any limit yet. 1 minus 4. That's negative 3. And then minus 4 times minus makes a plus 4 cosine squared. Good. Good. All right. Downstairs, what do we have? 2 root 3 cosine theta minus 3 times 1 plus 2 sine theta. All right. Now, things are starting to get interesting. What can we do? Well, it might help us I always like to be an optimistic person. Let's put the positive term in front. So we have limit as theta goes to pi over 6 of 4 cosine squared theta minus 3 over, and then there's this other stuff, 2 root 3 cosine theta minus 3, 1 plus 2 sine theta. Now, we start thinking, I need to do something to try to get a cancellation. I really want to find something upstairs among this 4 cosine squared theta minus 3 to look like something downstairs. Well, which means I'm really trying to say, is there anything that looks like 2 root 3 cosine theta minus 3? At first glance, it appears not so clear. But that's our first glance. We should take a second glance. Do you see something? Here's something to think about. I really think, boy, it would be nice to get this as a cosine theta. So it'd be somehow nice to sort of factor it, right? And does it factor? Now, it doesn't look like it right away. But remember, in the back of our head, we have our good old reliable friend, a squared minus b squared, which is a minus b, a plus b. I can think of 4 cosine squared theta as 2 cosine theta squared. How about 3? I can think of that as square root of 3 squared. So I got a squared minus another squared b squared. That means I can use the formula. Okay, that's something. So this is going to be limit as theta goes to pi over 6. So upstairs again, a minus b, a plus b. So 2 cosine theta minus root 3. And then we're going to have 2 cosine theta plus root 3 downstairs. Now, before we write it down, we say, it's looking pretty close to this, except there's a root 3. Let's just pull that root 3 out. Okay, we can do that. Hello, root 3, you're coming out. So that'll be 2 cosine theta. Now, if I pull a root 3 out of a 3, what's left? The answer is a root 3. 1 plus 2 sine theta. And now we're like, we see what's happening. Now we have things which we can actually cancel. And that means that we've been doing something right. We cancel off these pieces. And now we have something where we're almost there. We're almost home free. I'll go ahead and rewrite it one more time. The limit as theta goes to pi over 6 of 2 cosine theta plus root 3. Downstairs, root 3, 1 plus 2 sine theta. Now, plug in pi 6. Let's hope things don't cancel. Cosine of pi 6 is root 3 over 2. Root 3 over 2 times 2 means that we're going to get a root 3. Then there's another root 3. Downstairs, we're going to end up with a root 3 times 1 plus 2 times sine of pi over 6. Sine of pi over 6 is a half. So 2 times a half is 1. So we end up with 2 root 3 upstairs, 2 root 3 downstairs, meaning our final answer. Wow. 1. Wow. Well, I guess sometimes 0 over 0 does equal 1, but not always. So what do you need to do? Do the work. Do the work. Good. Good. This was fun. I like that one. Okay. One last question. And here it's true or false. So we got a 50-50 chance. Is the following true or false? If the limit as x approaches a of f of x is equal to b, and the limit as y approaches b of g of y equals L, then the limit as x approaches a of g of f of x is equal to L. Now there's a lot here to parse, so let's think about what we're saying here. What we're saying here is that f is getting close to b. Okay? So as x is close to a, the function f of x is close to b. So in other words, another way to phrase this, let's say it a couple ways so we can get it right. If our input is getting close to a, our output is getting close to b. All right, now here, the limit as y gets close to b, g of y. Now this says if our input is getting close to b, our output is getting close to L. So what's happening here? The limit as x goes to a of g of f of x. This is one of these problems, I kind of like to call them an onion problem because it has layers. And also like an onion, there might be a couple of tiers involved. Okay, so what do we have? So we see that x is getting close to a. So that says this layer here is getting close to a. All right, so far so good. The next layer is the f of x layer, all right? Okay, the f of x, since x is getting close to a, f of x is getting close to b. Okay, so far so good. Now, the last layer, if the input is getting close to b, then g of something close to b is getting close to L. So, okay, well that's pretty good. Wow, that was easy. So it should be true, right? Right? No, it's false. Wait, what? Hold on. What's happening here? Why could it possibly be false? Okay, so there's a catch here. I will tell you that if you show this to a lot of mathematicians, they'll even hesitate because they know the answer should be false, but it's not so clear right away why it's false. So let's be really careful. Because I said something which was a little bit misleading. All right, so what did I say which was misleading? I said the following. As x is getting close to a, the function is getting close to b. Now that's a true statement. But here's the thing, is when I'm taking the limit as x is close to a, I can't have a go inside. All right, that's fine. So the first layer is okay. So this first layer is perfectly fine. It's true that this inside layer is getting closer to b. There's no surprise there. But here's the stick, the part that makes you go, huh? So remember, what do we have? We need to have that this part right here, it needs to get close to b, but not b itself. That's how limits work. Limits say, I'm getting close to this value, but I'm not looking at the value itself. So the problem is we don't know if we have control where the function is itself, whether or not it's b or away from b. So let's be really explicit and show an example where things may not work out. So in fact, what we're going to do is we're going to have let f of x equal g of x equal the following function. It's going to equal 0 if you're not 0, and you're going to be 1 if you are 0. So if you were to graph this function, it's a really easy function to graph because it's almost always 0. So the way we graph that is we put a little tiny hole, and at 0 we're up at 1. Okay, so let's check a couple of things. First off, let's figure out what happens here. What's the limit as x approaches 0 of f of x? Well, as I'm approaching 0, what happens here? As I'm approaching 0, what is the function doing? Well, it's always 0. And so this is really the limit as x goes to 0 of 0, which is 0. Okay, so now what have we done? We've identified things. So let me be really clear here. This part right here is our A, and now this is our B. So what's the limit as y goes to 0, because that's our b, of g of y? Well, it's the same function. And therefore, we're still going to have the same behavior. We're still going to get 0. So, what do we have? Well, we've now come to the conclusion that this is our value for L. Okay, so far so good. Now, let's think about the following function. What is g of f of x? So, there really are two cases. Suppose I pick a value which is not 0. Then f of that value would be 0, which means I'm plugging 0 into the inside function. Now, when I plug 0 into the inside function, what do I get? Well, I get 1 out. So, this function is 1 if we're not 0. Now, suppose we plug in 0. If you plug 0 in, so f of 0, according to the rule, f of 0 is 1. G of 1 is 0, so it's 0 if x is 0. So and somehow what happens is this does the exact opposite. So sort of like if we were down here, then all of a sudden we've jumped up. So the graph of this function looks like the following. And there you go. Now, what happens? So, what's the limit as x goes to 0 of g of f of x? The answer? Well, as we approach 0, we're always 1. So that's the limit as x goes to 0 of 1, which is 1. And now it turns out that 1 and 0 are not the same. True story. 1 and 0 are actually different numbers. And so this is a false statement. So you got to be really careful here. Now, you might want to ask the question, is it ever true? And in fact, there's a beautiful idea. So there's something called continuity. So the idea of continuity is that you don't have any things where there's jumps or gaps or missing pieces. See, there's a sort of like part where you have to like, boom, jump up and then keep going back along. When you do have continuity, you can say that it's a true statement. So if we had added some extra conditions to f and g, it's a true statement. But you have to make sure you have the right conditions. Now, if you've ever wondered why mathematicians are so paranoid about proofs and like justification, it's because we know weird things can happen if we're not careful about making our assumptions, and we have to think about things. This idea of calculus, it took actually quite a lot of time to evolve it and make sure we understood it properly. And so you're benefiting from centuries of thought, and hopefully you're taking advantage of all that hard thinking that your calculus forebears did for you. All right, well, that's a lot of practice with limits. Good. Hopefully we're pretty good with limits. Well, don't worry. We're going to do more. There's more to come with limits. So, all right. Have a good day.